Hello and welcome to another walkthrough. Now this time it will be Edexcel IAL S2 June 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of times, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Okay, here's the S2 paper, June 2025, and I'm going to start the timer now. Okay, let's go. Number 1, continuous random variable. Just going to do here. Okay. The continuous random variable x has cumulative distribution function given as that, right? And k is a positive constant, show that k equals 1 over 5. Okay, so because basically this is just one piece that is relevant, because the 0 and the 1 we don't count. So that means if we substitute the upper bound of the domain in this function, we should get 1, because that's what cumulative is. Yeah, it's like you add up probability and equal to 1. So I'm just going to substitute this, yeah, and then equate it to 1, because that's what it is. Yeah, okay. So k times, inside here you have 6 minus 1, which is 5. So yeah, k is 1 over 5. That's just 1 mark, simple. Part B, find p of x greater than 0.6. So we can use the cumulative. This is basically finding the probability from x equals 0.6 and to 1, right? So this is going to be f of 1 minus f of 0.6, yeah? So it's like doing the 1 minus the f of 0.6, you're going to get the right tail. If you put f 0.6 alone, that would be p of x less than equal 0.6, right? And we already know that f1 is 1, so this is 1 minus f of 0.6, so k is 1 over 5. I'm just going to substitute 0.6 in the equation there. Okay, like that. And then we're going to use a calculator. So 1 minus 1 over 5 times 6 times 0.6 to the power of 2 minus 0.6 to the power of 4. That would be the answer there. So yeah, 0.534 would be 3 significant figures for that. Let me just double check the calculator work here. That should be fine. I'm happy with that. Okay, so part B is done. Part C, I show that the median m of x satisfies this. So the median happens when the probability from the left tail is equal to 0, or the right tail, because it's either way it's just 0.5, right? So we are finding that the median m, so we do f of median will give us the 0.5. Yeah, so basically if we substitute m into the x there, k already known to be 1 over 5, so 6m squared minus m to the 4 should be put equal to 0.5, right? Yeah. And because a, b, and c are integers, so probably I have to multiply everything by 10, because this is basically 1 over 2. Let me change that to 1 over 2. So as you can see, the lowest common multiple of the whole denominators would be 10. So if I multiply by 10 across, right, I'm going to get 12m squared, yeah, because when you multiply 10, you have 2 there. And then minus 2m to the 4, and this is equal to 5 after multiplication. And if I do on the same line here, yeah, it seems like I have everything. So I have 2m to the 4. If I move everything to the left side, to the right side, minus 12m squared plus 5 equals 0. So that would be the answer to part CI, yeah. And CII, hence find the value of m. Yeah, we're just going to solve that quadratic. Well, it's kind of like quadratic, but you can let m squared be something else. But I'm just going to go factorize in terms of m squared like this, yeah? So rather than x, you have m squared when you quadratically factorize that. So we're gonna have 5 and 1, I guess, because that's multiplied to 5. So minus 1 and minus 5 here multiply to 5, and the middle term you get minus 12, so that works. And then we're gonna solve to find the value of m. Note that m should be something that makes sense between 0 and 1. So the first one, m squared equals 1 over 2, or m squared equals 5. Well, this one will give you plus or minus root 5, which is greater than 1. Root 5 is greater than 1, so that doesn't make sense, right? So we would have m equals plus or minus square root 1 over 2. Well, the one that makes sense should be the plus 1 over root 2, right? So therefore, m equals 1 over root 2, which is, if we plug in the calculator there, 1 over root 2, that would be 0.707, yeah? That's the value of m. Okay, part D. Find using calculus the mode of x. Well, the mode happens when the density, or the PDF, or the lowercase fx function is maximum. Okay, so for mode, fx is maximum. And how do we find this? Well, we need to differentiate this function, but we don't know the fx yet, so we need to find the fx first. How do you find fx from knowing cumulative? Well, you gotta ask yourself how you would have got cumulative in the first place. You would integrate the PDF, right? And the PDF is the lowercase fx here. So that means if you want to get back to the PDF here, you need to differentiate, right? So fx is just the derivative of cumulative function. So I'm just going to pick the middle one there. So it's just 1 over 5. You differentiate the inner part there. So it's going to be 12x minus 4x to the power of 3. Okay? And there is only one significant piece here, because it's, just one distinct one. The 0 and 1 doesn't count much. So here we have the PDF already, and we need to find maximum, so we do d by dx of that PDF again, yeah? So I again have 1 over 5, 12 minus 12x squared, right? So I'm going to put this equal to 0 and find the maximum, right? Because it seems like I can here, basically, because it's quadratic now. So this is then, if you put that to 0, so you have 12 minus 12x squared equals 0, right? And then, well, x is just plus or minus 1, right? To make that work. But x minus 1 doesn't make sense, so it's actually at x equals 1. Exactly. Yeah, let me just double check my math here, because that's exactly on the edge, right? At the bound. If it's not coincident, then okay, let me just double check the integration of differentiation. So 12x, 4x to the 3, and I differentiated that again. I get this. Yeah, I think it should be fine. So that means the mode should be 1, because that's at, when you have x equals 1, here is at the maximum of PDF. Yeah, so that should be fine. Part E. Given that EX, expected value of X, is 0.64, so that's kind of like the mean, but in continuous random variable, E expected value of X is just the integral x of x dx, and you got to go through the bounds there, 0 to 1 in this case, yeah? And we are given that it is 0.64. Now we're gonna, wait, hang on. We don't need to find it, we got it, right? Oh, sorry. I mean, if we did find that, then it would be the same value. Now we just compare the skewness, sorry, okay. So the median was 0.707, right? So 0.64 is smaller than 0.707. So that means mean, yeah, which is the expected value here, is smaller than median. Well, if means was greater than the median, then it would have been a positive skewness. But this is the other way around, so this is negative skewness, yeah? Okay, that's it. And that's it. So we say mean less than median. That's the reason, actually. So this is negatively skewed. Okay, so question 1 is done. Let's do question 2. Okay. On Friday evenings, a shop opens from 7 p.m. to 11 p.m. During this time, customers are known to enter the shop at the mean rate of 20 per hour. A, state a suitable distribution to model the number of customers that enter the shop on Friday evening. So, suitable distribution, this is a constant rate of occurrence. What is the occurrence? Well, a customer entering a shop. So, this is Poisson distribution, right? Poisson's distribution, that's it. And suitable distribution, well, just to be safe, yeah, so we're just going to have to do PO and put everything in 20 per hour. Oh, 30 minutes interval, so it's just half of that. So if this is per hour, then if we divide that by 2, we get the rate at 30-minute interval. So this is perfect, yeah, that's it for the answer to B, to A. State a necessary assumption for the model in part A to be valid. Well, you have 3 main characteristics for Poisson: independent events, in this case, independent customers entering the shop. So that means individual customers, or all customers that are to enter the shop on that particular time interval, are independent. It means that if person A enters the shop first, it doesn't influence the next person to enter the shop, right? I mean, in the real world context, I mean, if you see someone weird entering the shop, you might not want to go into that shop. I don't know, maybe, yeah. But these are independent, right? The second one is that only one single customer enter the shop at a time. We can also use that. And the third one, the constant rate of occurrence. But we already talked about the constant rate here. So I'm just going to go with the second one because it might not be that trivial. So only one customer enters the shop at a time. Yeah, no more than one, right? Okay, part C. The manager makes alterations to the shop's layout. Following these alterations, the manager wants to find out whether the mean rate of customers entering the shop has changed. To this test, the manager decides to monitor the number of customers entering the shop the following Friday. The manager randomly selects 30-minute interval between 7 and 11 p.m. Okay. Write down the suitable null and alternative hypotheses that the manager should use, right? Okay, so H node would be, because this is Poisson, so we're just going to do lambda. The null should be just equal. This is 30-minute interval, so we're just going to do 10, right? And alternative would be lambda. Well, because the manager wants to find out whether the mean has changed. So this is just two-tailed hypothesis testing. Okay, and I think I'm done with that. Part C. Part D. Using 3% level of significance, find the critical region. Okay, so each tail, because this is two tails, so each tail is 0.015, right? Yeah, just 3% divided by 2. And then, so we have lambda being 10, just the maximum lambda. You can open the table there. So we're going to find, you know, I mean, I would like to draw it as a bell curve, and then you would look at 2 sides there where is the value x1 here, where p of x1, x less than equal x1 would be less than 0.015%. I mean 1.5%, sorry. And this area here, x2, where p of x greater than equal x2, also less than 0.015%. But because the table doesn't show the 1 greater than, we need to convert this to less than equal x2 minus 1. So we go 1 less, right? Greater than, and then you need to subtract this from 1 to find the other side. So that's 0.985 instead, right? So let's keep this and look at the table. So I'm just going to open the formula sheet. Oh, that's not the formula sheet, is it? Let me just change that. Okay, it should be this. Yep, okay, so formula sheet, we go to Poisson table. Should be after the binomial, I guess. Yep, so we look at 10 here and this column here, this column. So we want the less than 1 first. So I'm just going to write px less than equal, well, we want the one that is less than 0.015. So this one is the first one that is less than, so I'm just going to write p of x less than equal 3, 0.0103, but we can't just write this and take it. We need to show that, okay, it's actually the first one, so we go to the next one and show that it's already greater than here. Yeah, and that's why this one is convincingly the right one, okay? So we put an asterisk there, and then for the other tail, we want the one that gives you greater than 985. The first one gives you greater than 985 is this guy, so that's 17. So I'm just going to say p of x less than equal 17 is 0.9857, and the next one, which is this one, will not work because it's not greater than 0.985 yet. 985, yeah, but this is 9730, so we take this one. So this one would be, the critical value is x less than 3 for that one. Well, we go for this one, but remember 17 here is going to be x2 minus 1, so actually x2 yeah, is x2 is 18, because we need to go one more to the other side. So that's x greater than 18. So critical region would be actually x less than equal 3 or x greater than equal 18. Okay, to be critical there. All right, critical region. Okay, so I'm just going to take back the paper. And then we're done with part D. So part E. Okay. Part E, find the actual significance level of this test based on your critical region from part D. Well, we basically add up the probability there. So from the first part, it's just 0.0103 and add with the probability of 1 minus this one. So 1 minus that, yeah. Okay. So that would be equal to, if I do a calculator, right? 0.0103, and the other one plus 1 minus 0.9857. So that's actually, yeah, a little smaller than 3% basically for both. Oh, I copied the number wrong. Yep, should be that for part E. Part F, during the 30-minute interval that the manager monitored 16 customers entered the shop. Comment on this finding in the light of your critical region in part D. Well, okay, so just basically using that to just determine whether we reject or accept null hypothesis. Yeah, 16 customers is not in the critical region. 16 is not in the critical region, CR. Yeah, I just use CR there. So so we accept, we don't reject, we accept H0, right? So that means the manager's belief, right? I'm just going to get the context here. Manager decides to monitor the number. Manager randomly selects. Manager makes alteration. Manager wants to find out whether the mean rate. Okay, so there is no evidence that the mean rate of customers entering the shop has changed because it's not critical. So yeah, that's how you conclude. Next question, number 3. Okay. A sweet shop produces different colored sweets and mixes them to sell in small, medium, or large bags. The proportion of sweets that are blue is P. Each small bag is filled with a random sample N sweets. Okay, the mean number of blue sweets in a small bag is 3, and the variance of number of blue sweets in a small bag is 2.25. Find the value of N and the value of P. Okay, the blue, right? So proportion of sweets that are blue is P. So it's like probability of blue here is P. each small bag is filled with a random sample n sweets. The mean number of blue sweets, so it's basically n times p, yeah, is 3. And the variance n times p, 1 minus p, right? That would be 2.25. So those two pieces of information will lead to these two equations, and we just want to solve. Now, I mean, if you plug 3 in here, it would be easier to solve for that. So I'm just going to write 3 times 1 minus p is 2.25, right? So that means p is equal to, that would be 1 minus 2.25 divided by 3 if you solve the equation, right? So 1 minus 2.25 divided by 3, yeah? So p is 1 over 4, or 0.25. Oh, and n is then, if we plug 1 over 4 into this, we get n equals 12, right? Yeah, that's it. The proportion of sweets that are green is 0.2. So we now know that the blue is a quarter, yeah, and the green is 0.2. That means we already know another one, which is, what's the other one? We have blue, green, no idea about the other one, colored sweets. Yeah, we don't know yet. Anyway, each medium bag contains a random sample of 40 sweets. For a medium bag, B, find the probability that the number of green sweets exceeds the expected number of green sweets. Okay, the expected number of green sweets, yeah, is going to be 40 times the probability of selecting a green sweet, which is 0.2. So that is 8. So if we do x, and this would be again binomial, n is 40, p is 0.2. So we want the probability that the number of green sweets exceeds mean greater, not equal. So x greater than the expected number of green sweets, which is 8. So this is actually p of just 1 minus p of x less than equal 8. Because it's greater than 8 and not including 8, so we do 1 minus x less than equal 8, yeah. So we're going to use the table. Yeah, I think the table can do that because it's less than 50. So binomial table, we look at n equals 40 here. And probability being 0.2, so it's this column here. And we go down to this one, so it should be this value, right? Yeah, I'm just checking. Yep, okay, so minus 0.5931, yeah, less than equal 8. Okay, so that's going to be 1 minus 0.5931, so 0.4069. That's the probability of number of sweets exceeding the expected number. Now let's go back to the paper. Part C, the proportion of sweets that are yellow is 0.1 now. Each large bag contains a random sample of 80 sweets. That's greater than the maximum n in the table. C, I, use a Poisson approximation to find the probability that a large bag of sweets contain at least 12 yellow sweets. So lambda is just n times p in this case, yeah? So that's 80 times 0.1 being yellow there, so it's 8. So we do from binomial 80, 0.1, approximated to Poisson 8, yeah, like that. We need to write that line, yeah, very important. So that means if you want to find probability that the large bag contains at least 12 yellow, so if we do x contains at least 12 yellow, so at least is greater than equal 12, yeah, a large bag. So that would be approximated to, well, that's equal first, 1 minus p of x less than equal 11, right? And that would be approximated to 1 minus, because we're going to do Poissons, right? Oh, hang on. Poisson 8, yeah, we can do Poisson 8. So let's take a look at Poisson 8. Poisson and lambda being 8, which is this guy right here. We want x less than equal 11, right? Because that's 12 there, so this is 11. So we put 0.8881 there. That's 8 and 11, yeah? Okay, so let's go back. So that would be approximated to 0.1119, right? Yeah, just all that. So that would be the answer for part CI. Yeah, happy with that. Second. Justify why a Poisson approximation is suitable in this case. Well, that's simple because n is large and probability of 0.1 is small. That's it. Those are the conditions for approximating from binomial to Poisson, right? You need to know that. Okay? Okay. That's it. Number 4. So far so good, right? Nothing too hard here. Maybe they're waiting for me at the end. A bag contains a large number of beads of the same size and shape. The beads are either black or white. Black beads and white beads occur in the ratio of that. In a game, a player takes a random sample of 3 beads from the bag. Player scores 4 points for each black bead taken, 1 point for the white. A random variable x represents the total number of points for 3 beads. Find the sampling distribution. So basically, you just, consider all the possible case. You just have black and white here, W and B, right? So I'm just going to do B, 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 W, and you have 3 cases here. So I'm just going to do 3 of them. Yeah, 2B, 1W, and you have 1B, 2W. Yeah, and then you can have 3W, right? So you have 1B, 2W, 2B, 1W, 3 W's, and 3 B's, and nothing else, right? That's it. Yeah, I'm just checking if I miss anything. Yeah, so basically there are how many? 6 and 8. So there are 8. It's like 2 to the 8, the number of cases here, because you have to select 3, but in each selection you have 2 choices. So it's basically 2 to the 3, and that works. So now the points on the BBB here, because for each black we get 4 points, so that would be 4 times 3, which is 12 here. Yeah, that's the points, and this is 2B, so 4 times 2, yeah, plus W is 1, so this would be 9. And this is 1B, 1 black is 4 plus 2 times 1, so that's just basically 6. 3 whites, we have 3, okay? And now we do the table. So if this is x, little x, and this is P of capital X equals x, then we have all the cases, right? So the points would be, the minimum point is that, right? 3 in order, that's 6, 9, and 12, yeah? All the possible cases where you can get the number of points. It's not about getting B's or W's, but it's about the total point here. So that's the variable x. So how do you get 3 points? Well, you need to get 3 W's. So how do you get 3 W's when? Well, 3 W's come from, so the ratio here suggests that it is 2/7 and 5/7, right? And because the number of beads is large, so we're not going to do subtract 1 when we select the next one. So basically this will just be the probability of each white, which is, so black is 2/7, right? So PB is 2/7, so P white would be 5/7, yeah? Black and white, yep. So this is 5/7 to the power of 3, okay? So I'm just going to do that. And this will be 3 times, so each one will be 1 black, so 2/3, 2/7, sorry, and this will be just 5/7 squared. This similarly will be, black is 2/7, so we do 2/7 squared first, and times 5/7. And this will just be black to the power of 3, and you only have 1 case there. So we're just going to fill in the numbers there. So I think I'm gonna do yeah, let's do exact value. So 5 to the 3 is 125. 7 to the 3 I believe is, what is 7 to the 3? 3, 4, 3 I think, yeah. Okay, yeah. And then for the 6, right, which is BWW is this one. So that's 3 times 2 over 7 times 5 over 7 to the power of 2. Yeah, 150 over 343. And now for the 9, which is this guy right here, we're just going to change that to 2 and that to 5, right? Just swapping them. So 60 divided by 343. And then the last one is just 2 to the 3 is 8, so 8 divided by 343. And if you add up the numbers on the numerator parts there, you should get 343, I believe so. 210. Yep, it is 1. Okay, and that's done for the sampling distribution. Part B, a random sample n sets of 3 bits is taken. Okay, the random variable y represents the number of these n sets that have a total exactly 9 points. Okay, so y is modeled, well, exactly 9 points, right? We are talking about this case here. Yeah, so this is binomial because you have a probability of getting 9 points to be 60 over 343, but you take n sets, so that's in trials. Yeah, and then we want the probability of y greater or equal 1 to be greater than 0.5, right? Okay, so probability of y greater than equal 1, well, with that probability, you can't really use the table. It's useless. But we can do something here because we know that probability of y greater than equal 1 is just the same as, I'm just going to write that. Well, it's the same as 1 minus probability of y less than 1, right? And y less than 1 is just y equals 0. That's the only case, right? And you want this to be at least greater than 0.95, sorry. So that means the probability of y equals 0, which we can find using the formula, must be smaller than 0.05, right? If you do the inequality there. Yeah, 0.05. So what is this, right? So basically you just use n, yeah, which is number of sets, and x here, which is 0, right? Yeah. The probability of success, which is 60 divided by 343 to the power of 0. Yeah, because we get 0 here, and 1 minus that to the power of n. This must be less than 0.05. Okay, and we want the minimum value of n to satisfy this. Okay, so this is 1, right? Yeah. So we have here, what is 1 minus that? So it's basically 1 minus 60 over 343. So that's 283 divided by 343 less than 0.05. Well, this is the power of n. Well, of course, you're doing S2, so I assume you know logarithms and log properties. So if you take log on both sides, yeah, you're going to have n log this, right? Yeah, you're going to have that. Just taking log on both sides. Now, it is important to know that when you do that, yeah, you want to solve for the n, right? You want to solve for the n. Now, only by taking log, you got to be careful. Because then when you solve for n, you want to divide this into both sides, right? But this is a log of some value less than 1. So this is a negative value. When you divide that, the sign will flip. So that means n would be greater than log of 0.05 divided by log of that whole thing. Yeah? Well, you can try plug this in a calculator. It's going to be less than 0. It's a negative value, basically. So So log of 0.05 divided by log of 283 divided by 343, and that's it. Okay? Yep, so n is greater than 15.579, blah, blah, blah. So we want the minimum value. That means n minimum is just 16 because it's got to be greater than 15.5. So that's 16 there. So 16 is the answer. Okay, that's it. Number 5. Okay. The continuous random variable x has a probability density function of that. Show that k equals 3.5. Again, yeah, we're going to integrate these and add them up and put them to 1, right? Okay, so yeah, nothing particularly hard here. Hang on. Right. Yeah, okay. So integral fx dx is equal to 1. So from lower bound to upper bound. But we're going to split, right? So that's integral 2 over 21x dx. This is from 0 to k plus integral from k to 6 of 2 over 15, 6 minus x dx. Yeah? This will be put to 1 to find the value of k. Okay, so the first one is 2 over 21. And if you integrate this, you get x squared, right? X squared over 2, so that's cancel 2 there. So it's just 1 over 20. And x squared, I'm just going to do that and just put 0 to k first here, step by step. This is 2 over 15. You integrate this, you get 6x minus x squared over 2, yeah? Okay. And then you're going to put the bounds in there. So this would be k to 6. We put that equal to 1. So the first integral, we sub k and 0, but the 0 will make that vanish. So we just have 1 over 21 k squared. The second one, right, so it's 2 over 15 first. And then if you plug 6 in, you get 36 minus, so that's 18 if you do 6 squared over 2. And then we got to do the minus, the lower bound, so that's 6k. And then minus minus, so we get plus k squared over 2 here equals 1. Yeah, and that's everything. Now you need to solve quadratic, basically. So, I mean, I'm spotting that this is, you know, the lowest common multiple of those would be 375, 105. So I'm just going to multiply by 105 across that. Probably not too smart there, hang on. Let me just simplify this first. So you have k is 12, k squared over 21 plus 72 over 15 minus, well, hang on. I can just simplify that to 18 first, right? And I'm going to get minus 36, yeah, over 15 there for the first one, minus 12 k over 15 and plus k squared over 15 equals 1. Yep. I'm just double checking. Wait, hang on. This should be a plus, right? That should be, yeah, that should be no minus there. And then that's minus. Okay. Well, yeah, still the lowest common multiple here is 105. So I'm going to multiply that. So 105 divided by 21, you get 5, right? So that's 5k squared plus 105 divided by 15, you get 7. 7 times 36, you get 252. So that's 252. Yeah, minus 7 times 12 is 84k. And then 7 times k squared is 7k squared. Oh, that is also 105. So 12k squared minus 84k. We subtract both sides, so we get 152. Subtract again by 5 would be 147. It needs to be 7 over 2. Okay, so if I can simplify by 6, right? Can I? 6. Nope. 3? Yeah, I can do 3. 3, so if I simplify by 3, I have 4k squared minus 28k plus 49 equals 0. Yeah. So let's factorize that. I mean, I'm supposing that the answer is 3 over 5, so it's going to be 2k and 7, like that. Right? Just my sense there. And the other one should also be 7, no? Oh, that's 2 times 2 times. Yeah, exactly. So this is minus and minus equals 0. There you go. Yep. So that means k is just 7 over 2 or 3.5. That's it. As required. Part B. Use algebraic integration to find expected value of x. So expected value of x is basically integral of x fx dx. And of course, we're going to go through all the domains. These are just 2 domains, right? So we already found that k is 3.5, right? So it's going to be, again, we just do the integral again. So integral 2 over 21. Now you have to multiply that function by x, so you get x squared instead here. And you're going from 0 to 3.5 instead. Plus, this is 3.5 to 6 now. 2 over 15. Well, 6, you got to multiply that by x, so it's 6x minus x squared instead here. Yeah. And then if you add that up, you're going to get the answer. So this is 2 over 21, and then x cubed over 3 here, putting the bounds of that in. And then this is 2 over 15, 6x squared over 2, so that's just 3x squared, right? And this is x squared over 3, and the bounds is just 3.5 and 6, yeah? So for the first one, 0 makes it go away. For the lower limit, we just do 2 over 21 times, I'm just going to do 1 over 3 here as well, the 1 over 3 there. But the x cubed is just 7 over 2 to the power of 3. Okay, that's for the first term, done. For this one, right, okay, well, we can do things like this. 3, and then I'm just going to do each set, getting the lower and upper limits in action here already. So it's just 6 squared minus 3.5 squared. Minus, yeah, 1 over 3, and this is just 6 cubed minus 3.5 cubed. You can do this too. Yeah, so for each term, you just do the 2 limits already in there. Yeah. Okay, and we're going to plug everything in there. Algebraic integration, yeah. So we're just going to sub everything in there. So 2 over, you know what, I'm going to do big fraction here, and 2 times 1 times 7 to the 3. Here we have 21 times 3 times 2 to the 3 is 8, yeah? So that's the first term there. And then the second term, plus 2 over 15, wait, no, 2 over 15. And then in the brackets, I'm just going to do a close bracket here already. So 3 times brackets again. That's 6 squared minus 3.5 squared, okay? And then minus, here we have a third. It's quite nested there, so you got to be careful. Times brackets, 6 cubed minus 3.5 cubed, right? Yeah? So that's 19 over 6, basically, just that. Okay. Okay, so that's it. That's E of x. I hope I plugged everything in correctly. Let me double check everything. 2 over 15, and this is, yeah, the brackets are right. Subtraction and everything are okay. Powers and everything, yep. So I'm just going to leave it at that. Part C, given that E of x squared is that. Okay, so var x, we need to know that this is E of x squared minus E of x minus overall squared, like that. Yeah, it's easy and simple here. Just do that. Minus, you've already got the E of x there, so you must follow through like that. If E of x, that value was wrong, then you get a method mark here at least, right? So we're just gonna equal like that and keep that as an answer. So I'm gonna do 277 over 24, yeah, minus the answer squared. So that's 109 over 72 or 1.514. Just put it as a decimal as well. And that's it. Number 6 now. Okay, seems simple, not too bad. The continuous random variable x is uniformly distributed over a to b. Given that blah blah blah, ex equals 6, a, find the value of a and the value of b. All right. Well, if the mean is 6, this is uniform distribution, so the mean is in the middle. So that means 6 is in the middle. That means if you add up the two bounds and divide by 2, you should get the mean. So a plus b will be 12 here for the first equation. And then because you are going from 2 to 5 and get the probability of 3 over 16. So that's basically looking like this. This is a, this is b. So 2 to 5 is maybe in between like that. Yeah, like that. So p of 2 less than x less than 5 here is basically, if we find it from the diagram there, it would be 5 minus 2 over b minus a, right? That's how you find the probability in in uniform distribution. And they're giving you that this is 3 over 16. Okay? So the 5 minus 2 is the 3, so the 3, cancel the 3 here. That means b minus a is 16. Or you can do the cross multiply there, and then you will know that b minus a is 16. So if I add up the first and the second equation, a will disappear, so I get 2b equals 28, so b is 14, right? Yeah, so if b is 14, then a is minus 2, isn't it? Because they add up to 12. Yeah, it doesn't say anything about the values of a and b, so it can be. And if we try find the mean, it's right, yeah. 3 over 16, yeah, everything is okay. So these are done. Part B. Find the value of the constant c such that expected value of that equals 3. Okay, so expected value of cx plus 1, if we use the S1 knowledge, this will be equal to c expected value of x plus 1. The same thing, so just linear coding here. So that is c times 6 plus 1 given to be 3. So basically c can be solved there. It's just 1 over 3, right? Yeah. So it's 2 divided by 6 is 1 over 3. Basically that. Easy, right? Part C. Find var x. So var x is basically, well, this is uniform distribution. So yeah, we need to know that it's b minus a or squared here. Well, let me check the formula sheet. I mean, yeah, you have the formula sheet. I'm just going to check just to be safe here. There you go. So uniform distribution, b minus x, b minus a squared divided by 12. So that's the variance of uniform distribution. Okay. Yeah, they just want variance. I don't know why. It's quite simple here, this paper, honestly. So 14 minus 2. I mean, but that's the thing. You have to be very careful, because if the paper is easy and you are very careless, you don't get low score. Because everyone can do it. And if you're not careful, then it's the game of being careful, right? For those who will, excel. Okay, so it's 16 squared divided by 12, yeah? So 64 over 3, that's the exact value. Yeah, I'm also checking here, just being careful, right? Let me check that again, 16 squared over 12, yeah? Okay, we got the exact value. Now we want to find e of x squared. Well, that's simple. That's just var x plus e of x overall squared. Because if we know the formula of var x is e of x squared minus e of x overall squared. So if we solve that equation, we get e of x squared as a subject. So that's just var x, which is what we got earlier, plus the expected value, which was 6, right? It's just from the question there, 6 squared here. So we're just going to do 64 over 3 plus 36. And that is just 172 over 3. Exact value as well. Okay, and then part E. Find probability of that. Okay, So probability of this, well, because it's in terms of A and B, so we need to just have a crack on that first. We already know A and B, so B is just, what was B again? B is 14 greater than A. A is minus 2, yeah? Like that, just put everything into the inequality like that and you solve it, yeah? So 3 over 2x greater than, if you add 14 on both sides, you get 12. And if you divide by 2 and multiply by 2 and divide by 3, you're going to get 8, right? Yep. So it's p of x greater than 8. So this will just be 8 minus a, which is minus 2, divided by b minus a, which is 16. Yeah? Yeah, b minus a is 16. And this is how you find the probability of a uniform distribution, yeah? In a uniform distribution. Wait, no, that's 8 greater than 8. So I need to go 16 minus 8 instead, rather than that. Yeah, it's on the right tail. Yeah? Is it? No, it's 14 minus 8. We have to do b minus 8, right? b is 14, yeah, on the right tail. Yeah, that's about right. So this is 6 over 16, which is 3 over 8, yeah? Yep, okay, everything is fine here. That's it. Almost the last question. I think this is the last one, right? Let me check. It is, okay. Not even an hour yet. Okay. Yeah, this paper is easy. I think you guys should be very careful on a paper like this because people can do it, most people. When purchasing a pair of glasses from an optician, customers are offered insurance to cover the accidental damage. Past records from the optician show that 30% of customers buy insurance when they purchase a pair of glasses. Okay. In a random sample, 40 customers who have purchased a pair of glasses, X represents the number of those who buy insurance. A suitable model for distribution of X. Well, this is, of course, binomial because you have a trials of 40 people, 40 customers, and then 30% of them is the probability of them buying the insurance, right? So suitable distribution, so X modeled as binomial, 40, 0.3 like that, yeah? That's it. B, state the necessary assumption for the model in part A to be valid. Well, part A to be valid, yeah, the independent events can work. So each customer purchasing a pair of glasses and also buys and also buying insurance is independent, basically, just that keyword there, from one another. Yeah, so that's the key assumption there, very important. The probability that fewer than our customers who have purchased a pair of glasses by insurance is less than 0.05. So probability of fewer than R, not including R, is less than 0.05. I'm just translating to math first. Find the largest possible value of R. Okay, so we are actually finding P of X less than equal R minus 1, less than 0.05. And we are just going to use the table, right? So let me just show the formula sheet here. Okay, so binomial. So we are looking at the number of trials of, what was that again? 40 and probability of 0.3. So this column here. Okay, this one here, yeah? You see the cursor, yeah? And we want probability of less than something to be less than 0.05. So it's this one. So we need to show that. So P of X less than equal, this is 4, right? Yeah. Equals 0. Wait, hang on. That's not, it should be this one. So I'm just going to write 6 here first. and that's 0.0238, and then we show another one again less than 7, 0.0553. So this is the first one that is, no, this is the first one that would just be about less than 0.05. So we asterisk that one. Yeah, let me just double check everything. I picked the right probability and the right trials here. Okay, so just go back to the paper. Yep, so we're gonna say that, well, because this one works, so that means r minus 1 equals 6. Yeah, just pair this up. That means r is just 7. So 7 is the largest possible value of r. Because if we pick this, wait, hang on. Largest possible? Yeah, that's right. Because that's just the one that is just less than. Yeah, the first one is just less than. So 7, r should be 7 here. Okay. A second random sample of 200 customers, that seems a lot, who have purchased a pair of glasses is taken using normal approximation to the probability that at least t of these 200 customers buy insurance is that. Okay, so we're going to approximate from binomial to 100, 0.3 to normal. So NP is 60, right? Yeah, 30% of 200 is 60. And then NP times 1 minus P, this will be the variance. So that is 60 times 0.7, so that's 42, right? So it's just 60, comma, 42. 42 is the variance, okay? So that's normal approximation there. And we want to find that the probability of at least T of these customers, at least, yeah, less than, at least is greater than equal T from 200 customers by insurance is that. Okay, so this will have to be continuity corrected first, CC. So if you go to normal, it would be then, because you are going greater than T there, so that means you're going to go T plus 0.5, right? So X greater than T plus 0.5 instead, yeah? No, wait, hang on. Because you need more area. That would be less than, minus 0.5, yeah? Like that, because you would go to the left a little bit to get a little more area. That's the concept there. Just do it such that you get a little more area in the distribution. Basically, that's continuity correction, right? And this, right, we want so this is equal to 0.9474. So that means we want to find the z value. Well, let's have a look. 9474, that we might be lucky to get just, you know, if you look at the bell curve, which is this table here. And if we look backwards, is there any probability that is 0.499474? Yep, exactly that. Yeah. So this is on the right tail. This will give you a z value. Well, or I can write P of z less than equal 1.62 equals exactly 0.9474 from the table. Yeah. Okay. That means we can equate the z value to this z value. So we find the z value, that's the x value, which is this guy, yeah, minus the mu, which is 60, divided by the standard deviation, which is square root of variance. Yeah, gotta be careful. And this is on the right wing already, so it's a positive value. We put that to equal to 0.9474. And if we solve for t, then that's going to be the answer. All right. So t will be 0.9. Let me just put back the question. 0.9474. Yeah, that's right. Times root 42. Yeah. And plus 60.5. Yeah. So that's the value of t. Let me just double check the calculation here. That should be right. So t equals 66.63985. I'm just going to make that t equals 66 4 decimal places, so that's quite long. 6399. Yep, 4 decimal places. Oh, well, that's correct to 4 decimal places. So we're just gonna do maybe 4 significant figures. I'm just gonna do that, yeah. Okay. At least t of these customers. Well, let's do round to an integer, yeah. That makes more sense. So 67 customers, yeah. Okay. And then we have part E, which is the last part in the last question. The optician decided to introduce a special offer in which customers who purchase a pair of glasses get the first 3 months of insurance free if they buy insurance. Following this, a random sample of 25 customers who purchase a pair of glasses is taken and 11 of them buy insurance. Okay. Test at 10% level of significance whether or not there is an evidence that the proportion of customers who buy insurance when purchasing a pair of glasses has increased. Okay, so we are doing hypothesis testing. So H0 would be proportion of customer who have bought the pair of glasses have buy the insurance. So what was that before? It was it's just 30, right? This is from the beginning, yeah. Okay, it's still 30, yeah. So H0 P, this is 25, so we're going to use P because this is binomial. Okay, so H1, there is an evidence that the proportion has increased, so P greater than 0.3, right? And of course X is just binomial, 25 comma 0.3, right? Because the number of trials changed to 25 now. Okay, so we can find a p-value, or we can find a critical region. I mean, let's find a p-value. So the p-value x, p of x, because this is 11, and 11 seems to be greater than the expected value. So if you multiply this and this is the expected value, so if the result from the sample is greater than the expected value, you're going to do the right tail. So x greater than equal 11, yeah. This will be how you find the p-value to compare with the significant level, is equal to 1 minus p of x less than equal 10, right? So let's look at the table of a binomial. At n equals 25, I hope we have that, and p of 30%, yeah. So 25 and 30%, there you go. Okay, it's this column here. So we want x equals 10, so that's just this guy here, yeah? Yeah, and 25, p of 0.3. So I'm just going to plug in 0.9022, okay? And then we just calculate 1 minus 0.9022. So that is just 0.0978. And then that will wrap up, because then we compare to the level of significance, which is 10%. So 0.90978 is less than 0.1. So this is significant. So H0 is rejected, right? Because it's significant now. There is then enough evidence to suggest that there is an increase in the proportion of customers who buy insurance when purchasing a pair of glasses. Please don't mind my handwriting there. And that's it. That's just to conclude everything. I don't think I'm gonna double check everything here again, so I'm just gonna take my chances. Gonna stop the timer now, and I'll be back in a bit. Yeah. So guys, I have marked the paper. I lost 5 marks. Mostly, actually all of them, are from silly mistakes. Yeah, they're very silly. They're very easy to spot. I think I've annotated the video. So let's go through them. This one, yeah, I sounded so confident, right, about factorizing it, but actually this is not right. The middle term is -1 and -10. That doesn't add up to -12. So I should have used the the quadratic formula to find the value here. And I mean, if you do find the value, the right value I think should be 0.671. Yeah, so this should be 0.671. Yeah, just use quadratic formula. So I think I lost one method mark and I lost the accuracy mark. But this one is fine, and this one, although wrong number here, but I mean, I still conclude the right way because I follow through the number down there and concluded the right way according to what value I got. Yeah, that was the first mistake, lost 2 marks. And the next one is this one. Another very stupid mistake because I copied the wrong number. It's 2.55, not 2.25. I mean, I just took a while to find what the mistake was, and yeah, I looked at the number, it's different. So all the methods were fine except the actual number, so I think this should be 20 instead. And accordingly, this should be, I think, 0.15, yeah, for that. And good that, you know, the following parts after that part didn't rely on the answer from that part. So I was fine here for the accuracy for the rest. And the last mistake is on the last question on this one. I have found the right value of z, which is 1.62, but this is for the case where, you know, you are looking at this area. So this area is not 0.9474, but if you look at the sign here, they want greater than. So it's impossible to be greater than this particular z and have 0.9474. So actually the bell curve would look something like this. The bottom line is you are at the left tail. This t minus 0.5 is actually at the left tail of the bell curve. So that means the z value should have been minus 1.62. And actually, look at what I did. I took the probability, equate that to z. Although I found the right value of z, kind of. I just flipped the sign there. And yeah, so I got the method mark, so I lost another mark here. So accordingly, if I solve for t, I should get 50. Yeah, stupid, right? And that's it. The rest, I got all of them. So let's go through individual questions, right? I think, yeah, to conclude, this whole paper is easy. And again, if you lose marks like I did here, surely I don't get 100% UMS here, I'm sure. Because as of the time of recording this paper, for this paper, there's no mark scheme yet. But I'm sure I won't get 100%. You guys can check, I'm sure. And this kind of level of difficulty really urges you that you should be very, very, very careful. Because if you make some mistakes, while other people who are very careful, they're going to nail this paper. I didn't quite nail this paper, did I? And then they're going to get good marks. A lot of people will get good marks. And if you are careless, you're going to get low marks, right? So that's the overview of the paper. Easy. There's nothing out of ordinary here, like everything is classic. Nothing sparking too much thinking here, I would say. Just very typical, like the textbook classic questions here. But yeah, let's go through them anyway. I'm just gonna stress out this tricky part that you should be careful. Nothing in question 1, I would say. Question 2, yeah. Question 2, yeah, you see, there are a couple of questions in this paper where they ask you about the necessary assumptions. So if you forgot about that, make sure you do know how to write the assumptions about binomial, Poisson, and normal, right? Because sometimes they can ask about why is this situation appropriately modeled as a normal distribution because it's symmetrical and so on, yeah. And this one is fine, right? Hypothesis. There are 2 questions on hypothesis testing, right? And yeah, just make sure you know how to find the critical values, critical region, because that's probably one of the areas where S2 can be confusing. make sure you know how to find critical region, particularly the right tail, because the thing that I did here, -1 and then +1 back. Make sure you understand that. Yeah, go back to that question and understand. And yeah, I wasn't careful for this one. I copied the wrong number there, and this should be fine. This is binomial, right? Binomial, binomial, and binomial all the way. And the last one is just Poisson approximation. There's no continuity correction there then for binomial to Poisson. Yeah, and don't forget, this is again asking about the conditions that would be appropriate from binomial to Poisson. Yeah, sampling distribution. In some papers, this kind of question is hard. Like, you need to think hard. What happens? Some papers even have 2 bags. This is just 1 bag, 2 to 5, but in some papers, they kind of like pick one beat from 1 bag or bag A and other 2 beats from bag B. I've seen that. So prepare for those kind of questions as well, but this is fine. Sampling distribution means you just write a table of all cases and probabilities of them, yeah, written down, calculated, show the calculation as well. I did there, see? And then, yeah, make sure you also know how to solve this inequality appropriately, because it's a log, it's an inequality with a log, right? So that can be tricky at times. Continuous random variable, there are 2 questions on this one, right? This one is textbook classic, yeah. So basically just find expected value, show that some constant is what, because you know that the property of C continuous random variable is that they add up to 1, the total probability. So that's what I did here, equate to 1, solve for that, get the K, and all other ones are fine in that part. Number 6, yeah, this is uniform. I mean, they could have done harder than this. They could have, like, there was an example, like a cutting example that it was in year 2022 or 2020. You can check the short there. I think I will attach in the description, like the short. It's a type of uniform distribution that can be the most tricky. Yeah. So make sure you have seen one of those at least, and maybe more of those if you have time, because probably they usually play with that. Like, okay, you have a strip of spaghetti and or something, or wire, and then you're gonna cut in half. I mean, not necessarily in half, just cut in 2 pieces, but the position of where you cut is uniformly distributed. Yeah, like equal chance of cutting everywhere. And then you're gonna do something to one piece and another thing to another piece, like that. There's questions like that you should check out. Yeah. Yeah, but this is classic. Nothing very applied here, if you know what I mean. Like, it's just asking to find typical values in the distribution. So this is easy. Yeah. This one might be the most difficult one. I mean, it's just long and texty. You might lose concentration here, particularly if it's the last question. So just, be careful and be thorough here on everything. So state the model of the distribution, the suitable model for the distribution that is asking the things like this. This is the assumption, right? And then part C, find the R. That should be fine, just inequality again. And I think this one might be, might be the hardest part in this question. It's just backward calculation to find the value of t. So you need to be careful also about the continuity correction. Don't forget, you need to subtract by 0.5 to apply continuity correction, and the z value you need to look up from the table. So this one, part E, hypothesis testing, so that should be fine. And that was it, guys. So if you find this video useful, as you have watched this far, why not give me a subscribe? And don't forget to check out other IAL Edexcel papers walkthrough. I have walked through quite a lot of them, and I hope to see you in the next video. Bye.